All right, we're continuing with our pulley worksheet. We're up to number 5. We have a complex arrangement of pulleys, forms what's called a block and tackle. Block and tackle is used to lift a truck engine, which has a weight of 740 pounds. Okay, so that's my resistance, my load, 740 pounds. The input force required to lift, my effort force, is 38.6 pounds. What is the mechanical advantage of the block and tackle? Okay, so they don't really tell me which one, but we only have a force ratio and a distance ratio, and since we only have forces, let's go with the force ratio, so we're actually finding actual mechanical advantage. So it's just going to be 740 divided by 38.6. 740 divided by 38.6. And we get 19.17. That is my mechanical advantage. Number 6. Block and tackle with a mechanical advantage of 48 is used to lift a piano 31 feet to the 3rd floor of a building. So my MA is equal to 38. So my resistance distance, okay, so is 31 feet. Although the arrangement of pulleys in the block and tackle makes it easy to lift the piano, it takes a long time because of the length of the rope that must be pulled to lift the piano a small amount. What is the length or effort distance of the rope that must be pulled? So my distance effort. So again, we're looking for MA, and now we have distance. We're doing a distance ratio. So mechanical advantage is distance effort over distance resistance. So basically, technically, we're looking for the ideal mechanical advantage. Okay, but we're solving for DE. So DE is equal to mechanical advantage divided by or multiplied by the distance resistance. And so we're just going to have 38 times 31 feet. 38 times 31. And we get 1,178. So that is a lot of rope. That did take a long time. So we understand that, oh my God, it did take a long time to pull all that stuff. All right, zooming on to number 7. Number 7, a block weighing 25 pounds is lifted via 2 pulleys as shown. Determine the pulling force if friction can be ignored and we ignore the weight of all the pulleys. So it's an ideal world because actually this pulley down here adds to the weight of that because you have to lift the pulley as well. So we're ignoring a lot of different things. So the block weight, so that's my resistance force, is 25 pounds. We want the pulling force, so that's the effort force is my question. And so again, we're going to have a force ratio. Okay, but we don't know this, but we do know the mechanical advantage. Even though they didn't tell me, it shows in the picture. So in the picture, how many ropes are opposing the force? This guy's just changing the direction, and these 2 strands of rope are the only ones that are actually affecting that. So my mechanical advantage is 2. And so again, mechanical advantage is a force ratio of resistance over effort, but we want effort. So my effort force is a resistance force over the mechanical advantage. And so my resistance force was 25 pounds. My mechanical advantage was 2. So my effort force is equal to 12.5 pounds. So not too, oops, good, so you can see it on the screen. Okay, so number 8 and 9. So number 8, a single fixed pulley contains 2 strands. Explain the role of each strand. So basically on 8, when we have a fixed pulley and we're going over the top of it here, this strand here is just what we pull on. It's changing the direction. It's something to grab hold on and pull down while we're taking this load over here and we're pulling up. So the first strand is merely something to grab hold of and change the direction of my effort force. So my effort is now going this way instead of lifting this object up. Okay, and then number 9, okay, now a single movable pulley, so now my pulley is down like this. And so we have rope attached, and now we're pulling up like this. This strand, it's kind of like this is my helper. The ceiling is also helping me out. So both strands are actually taking part of the load because now the load is hanging down here. Okay, so I'm pulling on half and the ceiling is also pulling on half. So it's helping me out. So I only have to carry half the load over here because my helper of the ceiling, or whatever that is up there, is also pulling with half that stuff. So they're both pulling strands, not just changing direction, but actually, applying force for lift. Okay, so a block that weighs 25 pounds is lifted via an arrangement of pulleys as shown. So let's get this down here where we can see. Let's turn the paper over so we can have some paper to write on. It's lifted, so my load, so my 10, my resistance force is again 25 pounds. The pulleys are shown over here. Determine the pulling force if friction can be ignored, and we ignore the weight of all the pulleys. It's an ideal world. So it's just like number 7. So we want to find the effort force, and so we're going to find the mechanical advantage, and we're going to look at this over here. And when we look at this, we can see that there's 1, 2, 3, 4, 5 strands, but this last one is not actually opposing this load, so only 4 of them oppose the load. So my mechanical advantage is 4. And so now we're going to go back to that same thing we just did it a second ago. We said that the force effort is force resistance over the mechanical advantage, and now we're going to take our 25 pounds and we're going to divide that by 4. And what is that, 6.25? Okay, pounds. So it just gave me an advantage of 4. All right, so let's go on to 11. 11 in the block and tackle system, explain how mechanical advantage relates to the number of strands. So you can see that these basically are fixed. So this one's changing the direction, and this one is actually pulling up on the load. And then this fixed one, it's kind of like this one's just changing the direction as this other guy's pulling up the load, right? He comes around here and goes back up there. So this guy's just pulling up. So it's really, these are just fixed, and they have mechanical advantage of 1, where these down here, both strands are pulling up, and so they have the mechanical advantage of 2. And so it's kind of like a compound machine with a mechanical advantage of 1 and 1. So 1 times 1 is 1. Mechanical advantage of 2 and 2. 2 times 2 is 4. So 1 times 4, it's just 4. Okay, so that's how we get 4 strands and a mechanical advantage of 4. All right, number 12, in a block and tackle system with an ideal mechanical advantage of 4. So 12, we have the IMA is equal to 4. The effort is measured at 25, so my force effort is equal to 25 pounds. The resistance when balanced is measured at 65 pounds. What is the AMA? Okay, what factors might account for the loss of energy? Okay, so if we're looking for the AMA, AMA is just equal to the force resistance over the force effort. It's my force ratio, and so it's just 65 pounds over 25 pounds. And now we do that mathematics there, oops, not times, how about divided by 25, and we get 2.6. So that mechanical advantage versus that one. Okay, so what factors might account? So what do we lose in energy? Right, so we should be able to lift 100 pounds. We're losing 35 pounds, force pounds of energy. And so where did all that go? Okay, so part of it, when you look at it, let's look at this picture again so I don't have to redraw or do anything. When we look at this thing, as we go through all this, there's friction around every single pulley. But also, as I'm lifting on here, these 2 pulleys are movable, so they are also a load. So part of my extra 35 pounds that I'm losing in energy is going to lift. So if this down here was, 65 pounds down here, maybe I'm losing, maybe these 2 guys here account for 20 more pounds just in the pulley, and then the friction accounts for the rest. Okay. How can we have pulley viewed as a lever? I think we've looked at this several times, right? So as the pulley goes through here and we have the strands coming off, where the strands interact with the pulley, that's really the only part that matters. That's where the action happens, is right here. So all this other strand going around the top doesn't really make a difference. And then the pulley goes around this axle, and so really we're acting. So it's just like somebody is, there's the axle. It's like somebody's down here pulling on this side, and somebody's down here pulling on this side. And so now all of a sudden, what is that? That's just a first-class lever, right? And then if you look at the one where we had it going in the movable pulley, where we went up like this, okay, now this part kind of just sits. right? Because the load is in here. The load's not out on the one side. So now I'm pulling up, but the load's pulling in the middle. So again, now that I make this, it's like we're moving. I'm pulling up here, and this is kind of the stuck part, and it's trying to move this lever up that way, right? But it's trying to go through this load, and so now instead of a first class lever, we have a second class lever. And then how can wheel and axle be viewed as a lever? So it's the same thing, right? We already looked at this. So it's the same thing. Where does it acting on? Where does my hand, where am I gripping, right? So if there was a handle on this thing, like I'm twisting it around, like I'm going around in a circle or something, then my effort force acts right there, but my resistance is in here, right? Because I have to go against some sort, because the axle's, not just a point, usually it's something bigger. And so this friction or this resistance I have to twist happens right here. I'm acting right there. And so again, it's getting kind of skinny in there. You have this thing I'm twisting around. You have where that force is acting at and where I'm acting. So it just becomes, again, another second class lever. Now, if it reverses, then it becomes a third class lever. And that's it. Easy peasy.